Hi, and welcome to another junior geometry video. We're going to chat about tessellations in this video. Now, tessellation of a flat surface is the tiling of the surface using one or more geometric shapes with no overlaps and no gaps. In the real world, tessellations is used in all sorts of applications for tiling. Most tiling that you see in houses or in places around are all tessellations. There is a very famous artist called M.C. Escher, born just before the 1900s and died, I think, around 1976. And he produced some beautiful artwork. A lot of it, not all of it, but a lot of it was based around tessellations. In the real world, we use tessellations for construction and for patterns and design. Right, so let's get into GeoGebra and talk a little bit more about tessellations. Let's start with triangles. This is an equilateral triangle, and you can see that an equilateral triangle will tessellate by itself, no gaps, nothing else needed, no other shapes needed, just that triangle. I'll show you why. If we know the angles in a triangle, if you've done your work on triangles earlier, you should know that the angles inside an equilateral triangle are 60. And if I add up all these 60s, that gives me 360, which is a full circle, which is why triangles will tessellate. But it's not just equilateral triangle. Actually, let me show you this. It's any triangle in the world will tessellate over and repeat itself. So we can tessellate with any triangle we want. It doesn't have to be equilateral. If I was to step into the world of quadrilaterals, the square will obviously tessellate over and over again. And that's because the square's got 90 degrees. 90 plus 90 plus 90 plus 90 makes 360, which is a full circle. But again, don't get fooled into thinking it's just a square. It is any type of quadrilateral. We know angles in a quadrilateral add up to 360, don't we? So that's why quadrilaterals can tessellate over and over and over and over again. If I stepped into the world of hexagons, six-sided hexagons, right? This is a regular hexagon, and you can see that the hexagons tessellate without any other shape needed. There's a reason for that, because if you've done the work earlier in this series on geometry and you've worked out the angle inside a regular hexagon, it's 120, and you should then go 120 plus 120 plus 120 makes 360. So that's why they tessellate without any other shape. Now, these things are really unique. If you've done any work on investigating bees and where they live, the beehive is all hexagonal based. If you look at pictures of beehives, they're little hexagons, and bees have cleverly worked out that hexagons tessellate, and it's one of the best shapes and strongest structures for tessellation, and it gives them the most amount of space inside their hives. So it's quite a fascinating area that bees have learned their mathematics through school. What about pentagons though? Pentagons, five-sided pentagons. Although this is a really cool structure and it does tessellate, you can see that a pentagon does not tessellate by itself. We need to introduce another shape, this diamond or rhombus here, for us to allow us to tessellate. And I'll show you why. If we have a quick look, if you've done your work on geometry, you know that the angles in a regular hexagon are 108 degrees, and 108 plus 108 plus 108 does not add up to 360. So this little space left over creates this cool diamond in here, and then with a pentagon and a diamond, then we could tessellate it to get this awesome structure here. All right, I think we've covered everything we need to for tessellations. There's no workbook exercise on tessellations, but hopefully your teachers can give you some extra work and some stuff to look at in tessellations. Great, thanks so much for watching the video.